Good morning, good afternoon, and good evening. Welcome to our data center system design and installation engineering. This is a level 2 course, and within this course, we would be talking about 5 modules. Module 1 is about simple electrical design. Module 2 is for electrical installation. Module 3 is for air conditioning design, and Module 4 is for air conditioning installation. Module 5 is for data center best practices. So this is an extension course, as I mentioned before, to our data center operation and maintenance for engineers and managers. So this is for the data center system design and installation for engineers. And this is a level 2 course. So let us start with this. If you have any question, you can always send your email to me. My email address is Peter Kwan, Peter Kwan, N for Nancy, and then 1689 at gmail.com. Okay, so if you have any question on this, please let me know. Okay, so let's start. So for this module 1, we will be talking about simple current and power calculation. Now, I must qualify this electrical system design is based on the British system, right? Because this is a common system in Asia. So the second one, we'll talk about the power loading estimation, how to estimate the power requirement for a place or data center. Number 3, we talk about simple cable sizing. And number 4, we talk about system protection design. Number 5, we talk about any Q&A. And number 5, we'll have a summary test. Okay, so let's move on now. So first of all, simple current and power calculation. Now we must understand power, P, is equal to the voltage times the current I. Okay, so P equals to V times I. P means the power in terms of watt. Voltage, V in terms the unit of voltage is V, single V. The unit for current I is ampere, A, okay? So, for example, for a 100-watt tungsten lamp at a voltage of 220 volts, the current I is based on the above formula, P equals to V times I. So, I equals to P divided by V. So, I equals to the current amperes equals to the P divided by V, or sometimes we use the power watt, right, divided by the voltage, V. So if we have 100 watt divided by 220 volt, we got 0.45 amps. Right, that's really quite simple, I believe, right? So by the same token, if we have a voltage V equals to 110 volt, then the current I now becomes 100 volt divided by 110 volt equals to how many? Right, something like 0.9 amp, I think. Right, if you make a calculation here, or almost close to 1 amp. So in this case, you can see that if the voltage is reduced, the current is higher, isn't it? So in the case of high voltage, for example, in terms of high voltage, we're talking about 1 kV or 11 kV, you'll find that the current is lesser. If the current is lesser, because the voltage increased, the current is less. That's why the cable size can be smaller. That's why sometimes from the power plant to the substation and substation to substation, once they step down the voltage, but still at high voltage, the current is smaller and the cable size is smaller. As you step down the voltage, the cable size becomes bigger and bigger. Now let's look at another example. If we have a 6,500 watt Cisco switch or server, single phase, so the I equals to 6,500 divided by 220 volts equals to 29.8 amp. Now 29.8 amp is almost close to 30 amps, and the cable size could be quite large, or really reasonably large, and a larger breaker is needed. Hence, we need a 30 amp power source. But here, why the current is increased? Because the power has been increased as well, right? The 6,500 watt instead of 100 watt, all right? So that's why the current has increased, and so is the cable size. Now, don't forget, we're working on a single phase at the moment. Now, suppose the 6,500 watt Cisco switch or 6.5 kilowatt using kilowatt, right? The 6.5 is changed to a three-phase supply. That means using three cable to supply it. I mean the three live cables, one neutral. So the situation can be different. For three-phase supply, the voltage in the UK standard supply is 380 volts, for example, and based on a factor of 1.73 for the three-phase root mean square value. So in this case, our formula might have changed to the current I equals the power 6,500 watts divided by the three-phase voltage 380 volts times a factor of 1.73. The 1.73 is the root mean square value as well as the star delta configuration of the three-phase cable. So if you divide this one, you find that you're only using 9.9 amp, which is much smaller than the previous single phase 29.5 amp. So what is that? What's happening? So don't forget, in this case, we're using one single cable, one live cable plus a neutral as a return. But in the second case, we are using three cables, as I said, because it's three-phase supply. Three cables plus one neutral return. You're supplying actually 3 times this current. Right, so one cable carried 9.9, the other cable carried 9.9 amp as well. The third cable also carried 9.9 amp. So if you multiply this by 3, you get back this previous one. But instead of one cable, one live cable, you use a larger cable, 29.8 amp cable. Now we use 3 smaller cables, which is still supplying for that. And in fact, the power, not the power, but the three-phase supply is more efficient and effective, right? Because it's smaller cable and also the current is less. Even based on the same distance, right, for the power supply from the source to the equipment there, the Cisco switch, right? The cable size are much smaller and more efficient. All right, so it's very interesting between single phase and three phase. Now let us bring in a more complicated case here for the CDC. As CDC means a data center, chiller sump pump of 1,500 watts with a power factor 0.8. Now in the previous case, we have never touched on onto the power factor, right? Because we have 6,500 watts here, Cisco switch. Mainly for Cisco switch, which is more like a resistance type of server, the power factor is equals to 1. However, but for this chiller sump pump, if it is 1,500 watts and the sump pump moves, as soon as a mechanical equipment or electrical equipment which moves or rotating, then there will be a power factor which comes in. right? This is called the power factor. So in most cases, the power factor is 0.8, assuming, and this is very similar to the pump efficiency, but not exactly the same. But pump efficiency is another factor which we need to consider in future. But for the time being, let's consider that power factor 0.8. The power factor actually means how much in terms of the proportion that the output power equals to the input power. When the input power comes in as 1, in this case, the output power is only 80%. Right, so let's see what it is, right? So again, suppose now we have a 15,000 watt sump pump, and because I equals to the power P divided by the voltage in the pass, when the power factor equals to 1, we don't need to care about the power factor. Or we have assumed that taken into the power factor because of the 1. However, if the power factor does not equal to 1, like most electrical mechanical plant which rotates, like fans, pumps, chillers, generators, right? So anything that moves or rotates, you have a power factor, either 0.8 or 0.9, or sometimes they claim 0.95 or 0.99, whatever it is. We need to find out from the catalog or from the supplier. So in this case, we have to modify the equation that 1,500 watts here divided by the voltage 220 divided by 0.8. This is divide. This simple means divide, right? So 1,500 divided by 220 divided by 0.8, you got 8.5 amp. Actually, it's more than if the power factor is 1. Right? If you take out this power factor, right? Assuming if this is 1, then you can use the 1,500 divided by 220 volt as we did before. You find that the current is only about 6.8 amp. But because of this power factor, something like the equipment is not so, there's some loss in the equipment due to friction, due to other harmonic, or due to other things, then you need 8.5 amps instead of the original 6.8 amp if we take away this power factor. Okay, so I hope you understand the importance of the power factor. Power factor is a ratio showing how much real power or active power that we can get from the input power or the incoming power. I hope we can have some explanation later on, right? Now, if this pump grew bigger to 30 kilowatts, suppose now we don't have 1,500 watt pump, we have a large chiller pump of 30 kilowatts. But for such a large power supply system or 30 kilowatt equipment, we have to use a three-phase supplies for more efficient, as we mentioned in the previous slide. A three-phase power supply is more powerful. I mean, in terms of the actual power, right? Not the voltage, but in terms of the more powerful to turn a rotating machine, right? Either motor, rotor, chiller plant, fans, pumps. We have to use a three-phase supply. And in actual case, right, anything more than say 3 kilowatts, you can use a three-phase supply already if you want it. So if we remember that if you use a three-phase supply, the cable size could be smaller, and breaker protecting the cable can also be smaller. So it is also more efficient to use three-phase than to single-phase, as we mentioned before. So in this case, our current I is equals to 30 kilowatts, which is the power here, divided by 380 volts, divided by the root mean square root of 1.73, divided by the power factor 0.8. Right, you'll find that it is 57 amp. Now, suppose Suppose, as we said, if this pump is to use single phase instead, right? That means this 380 become 220 volt, and this root mean square root does not come in. And with the power factor still stays there, for example, you'll find that the current is 171 amp. So what did you see here? Let me give you 1 minute to draw a conclusion based on this example. Think about it. Or 30 seconds actually. I'll give you 30 seconds to think about it. What can you draw from this example here? Okay, there are a few things that you can draw, right? So for example, if you use a single phase, as we mentioned before, the current for the same 30 kilowatt will become 171 amp, which is bigger than if you use a three-phase, which is only 1/3, right? So the cable size, as we mentioned, the cable size here, if you use three-phase, is smaller. The breaker protecting the cable also smaller, more efficient, more powerful. That's number one. Number two, you can see that actually, if you multiply this 57 by 3 times, you'll find that this is equivalent to 171. As we mentioned before, because you use three-phase supply, 3 cable to supply the power instead of 1 single cable. Hence, the cables can be smaller size here. So is the breaker. All right, so this is interesting, right? Now, on the contrary, if you have a device which is using a maximum of 5 amps, right, this time, if we do the other way around, suppose you have only a device, you have a device which is using 5 amps. What is the maximum power that it can have? Right? If you know about the, your hair dryer, or you know your fan which is using 5 amps, or your lamp is using 5 amps, how many watt that could be? So by the same token, P equals to V times I, something like this, right? Or I times V, doesn't matter. P in terms of unit watt or kilowatt, I is ampere, V is voltage. So we use the current I 5 here, and the voltage is 220, so that's why you got 5 times 20, you got 1.1 kilowatts. Amazing, isn't it? So this is why a 5 amp supply can only give a maximum 1.1 kilowatt equipment only, or 1,100 watt equipment. Suppose your cable or your fuse can only protect for 5 amp device. That means it can only provide for a power equipment of 1.1 kilowatt or 1,100 watts. And if you plug in something which is more than 1.1 kilowatt, something like 1.5 example, and thereby your cable will get hot, first of all. And so is the protection device. It might trip as well. Yeah. So in the next one, look at this. Suppose now we have a 13 amp rack socket. Rack socket means is the server rack. Suppose inside the server rack you put in some power bar there, 1 or 2, but each one can only provide 13 amp. So what's the maximum power that you can, maximum power of the servers that you can put in there if you only got 1 bar which shows 13 amp socket there? Well, based on the same equation, P equals to V times I, or I times V. 13 amp is here, the voltage single phase is 220, you got 2.86 kilowatts maximum. If you use 1 single bar of 13 amp socket bar, or 1 socket if you wanted. Right, most server racks, they have 2 bars, right, 2 13 amp socket bars, right? So no matter how many sockets on the bar, maybe 2 or 4 or 6 or 8 sockets on one bar. So one bar can only provide 2.86 kilowatts. If you have 2 bars inside the server rack, each have 5 sockets, for example, or 6 sockets, for example, inside the server rack, the maximum you can provide is 2 times this one, which is about, I think it's 5.7 kilowatt only. But most racks, right, I think the normal racks would be 2 kilowatts, 4 kilowatts, or at the most is 6 kilowatts, right? Or sometimes they can go up to 8 and 10 and 20, and the largest one I've heard about is 20 kilowatts so far. Sometimes it's 40 kilowatts. So anything which is more than 6 kilowatts, I believe you cannot use 2 bars of 13M socket bar anymore, because each 13M socket bar, no matter how many sockets in the bar, on the bar, you only got 2.86. If you multiply by 2 bar for 2 bars, you only got 5.72, which is not enough for 6 kilowatt. So anything more than 6 kilowatt, you have to use individual radio circuits, right? Single supply, single equipment. And that's for most of these high density rack as well. Whether it's anything more than 6 kilowatt, you want to have only one single radio supply. For the same token, you have 8 kilowatt, 10, 20, 40 kilowatt, you use one single cable to provide one machine only. Similarly, for the UPS, right, suppose you have a UPS which can provide 100 amps, then its power available from the UPS is P equals to V times I, which is 100 amps times 220 volts. And in theory, it's 22. If I'm correct, let me check. 100 times 220. Yeah, so it's about 22 kilowatts in theory. However, most of the servers, I think they have power factor almost equal to 1. That's why we said we assume power factor equals to 1. However, there's no such UPS in the market which serve 22 kVA. Right, so don't forget. So if your UPS load you require 100 amp, and you know the power is almost 22 kVA, then you go outside to whichever the company sells the racks to you or sells the UPS to you. You have to go and ask for the market, which in the market I think they have 10, 20, 30 kVA or more. Right, so in this case you may choose a 30 kVA to cover the 22 kVA. Right, if you need 100 amp, you never use this 20 kVA less than the 22 required. This is the supply, this is the required or demanded. All right, so this is quite simple, I believe. Now moving on, suppose now you have bigger now, you have a 300 kVA UPS. Let's go back to the question now. Suppose the UPS can provide 300 kVA. What is its current that can provide? By the same token, power equals to current times volt, I times V, or V times I. All right. Now for this 300 kVA UPS, K, that's why you need to multiply by 1,000 and divide by single phase 220 volt. You have how many amps? Wow, you have 1,362 amps. What size is that cable? Don't forget, right? The calculations is correct, but sometimes we have to apply our common sense. What size is the cable to provide 1,362 amps in theory? Well, this is interesting, right? But let's move on first of all. Now, because usually the UPS also got a power factor, as I mentioned, right? The ratio of the active or true power based on the incoming power of 100, you only got 90% there. So in a single phase, if you have a UPS which can provide 100 amps, I think, sorry, if you have a UPS which can provide 300 kVA, so what's the current available for that UPS, right? So 300 multiplied by 1000 to make it become the K to become 1000. But the power factor is only 90. Well, actually, there are two things here, right? First of all, we have not put in the power factor yet. We just put in 90% of the UPS low only, because you never want to low up the UPS to 100%. Right? You make it to 90% only. So that's why you multiply by 9, divide by the voltage, you'll find that 1227 amp, which is very similar to what we did before, 1362 amp, because you only want to load 90% only. You don't want to load more than 90%. Right? You don't want the equipment being overheated, full load. Right? You don't want to work yourself every day, 24 hours. Right? You want to have some spare capacity. Here we have not taken into account of the power factor of the UPS alone. We just want to say we only load the UPS to 90% only. In theory, or in actual case, you have to multiply another 0.9 here to ensure that, if the server is having power factor of 0.9. But most servers, luckily, is only 1. That's why here you will get rid of the 1 for the time being. Yeah? Okay, cool. Okay, so again, don't forget, this is based on a single phase 220. Right? Single phase, yeah? What happened in three phase? Well, in a three-phase case, I think if you supply three-phase here, I believe you'll find that you still got the 300 kVA here. The total power still 300 kVA, or you got 90% of the 300 kVA because you want to only loading up 90%. You don't want to load more than 300 kVA, or more than 90% of 300 kVA. You don't want to have full load. You'll find that this current, if we are using three-phase here, the current would be divided by 3 here, something like 409 amp, or 400 amp, make it easier. But it's a three-phase, that's why each cable is providing 400 amps here. Right? Each cable providing 409 amp or 400 amp for either three-phase or 3 separate single-phase circuits, which is just divide this by 3, basically. Yeah, it's very interesting here. And actually, I have developed a fast method to calculate the current, right? Because of this factor of 3, right? Single phase and three phase, we can use the factor of 3, right? But I'll show you some other times. Now, secondly, let's look at the power loading estimation rule of thumb. Now, in the previous case, item 1, we talked about the current, the voltage, the power formula, and a little bit on the cable size. But now let's talk about how to estimate the power loading of a bank, of a data center, of anything, an office, even a residential building. So very often we have to find out how much power is needed for the new data centers, office, or area in terms of kilowatt or watt, it doesn't matter. But some useful figures that you can consider is lighting is nowadays using 15 watts to 20 watts per meter square. Based on the per meter square, we use the metric unit. By looking at this, you know that we are based on the British system because we are using meter square, right? Of course, the lighting can further reduce. Nowadays, they may be talking about something like 11 watts or 10 watts per meter square because of the energy efficiency. However, in general, you need to allow a bit more, right? So say 15 to 20 watt for lighting should be okay per meter square. And also the power including normally the air conditioning AC, but except the computer room, the comms room. Remember, the comms room means the computer room or server room. Then both the power, like for your computer and all these things, and maybe including the air conditioning unit, you can allow for 40 watt to 90 watt per meter square. But of course, it depends on which country you're working on, what is the government standard there. But the 40 to 90 watt per meter square is quite a general figure that we can assume. If you have, now, you know why we want to accept the computer room, because this is only the general office area or a normal area. A computer room is a server room is a more heavily input with the server racks, right? With racks and cracks, right? The computer room air conditioning unit. If you remember, computer room air conditioning unit, they must be separately estimated, right? And please attend our separate course, right? With separate fees, of course, right? So, all right, but that's how you estimate the general power, general lighting, okay? Anything which is heavy equipment, heavy things, heavy racks, high density rack, heavy electrical and mechanical plant, we use separate the actual power required from the supplier or based on the catalog to estimate the overall power for this special equipment. You cannot use this general rule 20 watt or 90 watt per meter square to estimate this. No, you cannot. You need the actual power requirement from the catalog. Now, suppose we have a data center office area in Tokyo, which is of 10,000 square feet. All right, 10,000 square feet. First of all, we must divide that by 10 to make it 1,000 meters square roughly per floor. So the power required per floor, power equals to V times equals to the because it's kilowatt, right? So the 1,000 meters square becomes here, and then 20 watt for lighting and 90 watt for air conditioning, not counting the server room, just the office area. You can divide by 1,000 to make it become as a kilowatt. Now this is not P equals to V times IR. This is P, the total power equals to the 1,000 meters square and 20 watt per meter square for lighting maximum and 90 watt per meter square for the air conditioning and power altogether. You'll find that this floor would use 110 kilowatts, as big as that. And that is the normal power supply required, excluding any crack unit or comms room equipment like the UPS and other, even fire security system. That need a separate calculation. All right. Now the essential power is much smaller than this 110 kilowatt originally for this non-server room area. But the essential power sometimes is also for smaller, is much smaller, and mainly for critical systems like server loads, crack units, fire, emergency systems, security system, all these things. Right? That's why you want to have essential power. Right? If you remember our previous course at level 1, the data center operation and maintenance course, this crack unit and fire emergency server load, this would be using the essential power, right? And for the IT load, server load, computer load, or security system, you may use the UPS. But once the normal power breaks down, like the power from the supply company breaks down, the UPS go out first. As we said last time, the UPS would immediately, without any breakers, provide the power to the critical equipment, like the server racks, circuit system, and all these things. The crack is not on UPS, the crack is on essential power. So after 15 seconds, when the genset comes in, the essential power will go through all the essential cabling, provide to the IT load, provide to the fire system, provide to the emergency system, provide to the crack unit this time. Right, but the crack is not on the UPS. All right, if you remember, if you have not, if you don't, well, please go back to our course for data center operation and maintenance, which is a level 1 course. Now, next slide talking about the server rack. Now, suppose we should allow for 2 to 2.5 kilowatt per rack in general. Nowadays, I think the servers are more efficient, although they are getting bigger and bigger and high density. But allowing for 2 to 2.5 kilowatt per rack may be initially okay, so long it's not a high density rack. That is for the case where you don't know, right? You only know about how many number of racks. You don't know about the actual power required. But if you know the server equipment is known, of course, we'll base on the actual kilowatt or actual watt from the catalog of the equipment instead. But if you don't have this data initially, from the very early beginning, you can use the take the minimum should be 2 to 2.5 kilowatt per rack, or you want to add more to say 4 kilowatt per rack. It's up to you. For future expansion and flexibility, yeah. But don't overestimate and don't underestimate. That's the difficult part of it. All right. Now, as we mentioned before, the crack power should be obtained from the supplier. You need to find out from the supplier who you want to buy the crack from. But don't forget, normally 1 kilowatt electric unit can provide to around about 5 kilowatt cooling, right? Based on the screw type, piston type, centrifugal type, roughly about 20%. So if you know about the kilowatt cooling, you divide that by 5, right? That's the kilowatt electric. Yeah. So suppose we have 100 kilowatt cooling required, then your current is likely to be only 20 kilowatt if you divide by 5 over the 100, right? So that's a rough calculation there. How much? Don't mix up the kilowatt electric and kilowatt cooling. They're two different things. Now, another simple estimation is you may want to allow for 5 amps for each desk, right? Again, for your computer desk or your desk, right? Which mostly computer, which is very small, normally is 68 watt or less than 100 watts. Telephone and mons, the mons again is very small. No matter how many mons you have, 5 amps should be enough because 5 amp can provide almost 1 kilowatt. 1 kilowatt per desk is quite a large, right? Large power supply already. And this does not account for other lighting or AC power for this desk. Okay, so if they, if there's any heavy electrical lighting, this is only for the power, of course, right? It does not account for the lighting over the desk or for any other air conditioning. Here, the AC means the air conditioning, right? The air conditioning, right? Okay, your desk does not need air conditioning basically, so that's why it does not include that one. All right, and then we go on to item 3, which talk cable size. Can talk about this one. Let us look at this one. This is a table which I extracted from the web, but make it up by myself, right? So for example, a 10 amp power equipment, right? Or the MCB rating is 10 amp. The cable size normally require 1.5 millimeter square. And the cable which can provide a maximum current of 17 amp maximum. But of course, it's based on the distance, right? It's based on the distance. The longer the distance, the higher the voltage drop, the lesser the current can be provided, and more cable size required. Right? Okay, so but this is for a single phase, 1.5 mm square. Now suppose you use a three-phase cable, then each would provide for 1.5 mm square, each cable can provide 15.5 m maximum per phase. All right, this is a single phase, this is a three phase, okay? Based on the, now this time based on the 1.5 mm square. Right, this is a MCB rating. If single phase for this, for three phase, then of course the MCB rating could be different. Okay, by the same token here, a 2.5 mm square cable requires a 20 amp MCB rating to protect the cable. The maximum that the cable can draw with a single phase is 24 amp maximum. Or you will ask, how come the cable size current is bigger than the MCB rating? Well, that's exactly what you wanted, right? You want the cable size rating, here in this case 24 amp, is bigger than the 20 amp, such that the MCB rating may trip if there's an overcurrent of 21 amp, while the cable size can still maintain that within his capacity. That means the breaker or MCB trip first before the cable being burned out. Now for the 2.5 mm square cable in a three-phase supply, it can provide 21 amp. And by the same token, for the 30 or 32 amp ring circuit, which is a ring, that's why it's 2 times 2.5 mm square, right? And then the maximum 24 amp each cable. You have two cable here because it's a ring. All right. For the 20 amp radial circuit, radial means single, direct from one point to the other point. Ring is a ring. It's a loop. So a 4 mm square 20 amp radial circuit, the maximum single phase cable is 32 amp. If using 4 mm square cable for three phase cable, supply three cable to supply, the cable each can provide only 28 amp. 28, okay? By the same token, as 30 and 32 amp radial circuitry, you need a larger cable, which can provide you 41 amp if single phase, but three phase is 36 amp. Right, but forget about three phase first of all. Let's look at single phase. Will make it more easy to understand. If you have an MCB rating of 50 amps, you may need a cable of 10 mm square, because the cable 10 mm square can provide 57 amp maximum. And by the same token, 60 amp, you need a cable for single phase is at least 16 mm square and 76 amp maximum. You cannot go more than 76 amp maximum. All right. This column actually refers to, for this cable size, what is the current available that can provide it to the equipment, but three phase, right? So that means you have three cables. Now, Let us look at another example here. If we have a simple fan coil unit, air conditioning unit, right, with a 200-watt fan motor. In our previous simple calculation, I equals to the power divided by the voltage, 220, if we use 220, and then make a power factor of 0.8. So the fan is only using 1.13 amp. Very small. It's not for heating, just a fan. So that's why a fan usually is quite efficient actually, or the power consumption is lesser than air conditioning. And hence, for a 5 or 10 MCB and a cable size of 1.5 mm square may be sufficient to provide, because that's for simple calculation, right? Because now if you have a fan motor of 200 watts, based on the voltage and power factor calculation, it requires 1.13 amp. You go back to the previous cable here, you only need 1 amp, but here it can provide 17 amp for you. But you only need 1 amp. So that's why you might need an MCB rating of 10 or even less than 10, like 6 amp for example, which is well enough in your case for a fan motor of 200 watt, which only need 1.13 amp. Now suppose you have a crack of 30 kilowatt cooling. This is again 30 kilowatt cooling, KWC. Assume the power needed is only 1/5 or divide by 5. So you only got 6 kilowatt electric. So the power required for this crack unit is about 6 kilowatt electric here, divided by the power factor 0.8, divided by the voltage single phase 220 volt. So the single phase is equals to 34 amp. So what size cable is needed if a single phase for a 34 amp? Well, go back here. 34 amp single phase, you might need at least a 6 mm square cable, because the 6 mm square cable can provide 41 amp, but you only need 30 something, right? Yeah, you only need 34 amps, right? So 34 is less than 41 amp. You look pretty safe. Now suppose you have, oh, this is done now. Okay, so this is done. Let's move on. However, the cable sizing is much more complicated than this. There's a lot of factors that you really consider, like the protection break or fuse. Using the protection device, right, is one factor. The cable grouping together, how many cables being grouped together, right? If you have a bunch of cables and a single cable, live and neutral return is quite different. Because if you bunch the cable together, the cable cannot release its heat, especially the inner surface of the cable. All right. There's also some other factors, like if the cable is concealed or open installed in the air or through the ambient temperature. So again, the ambient temperature is important, and the cable, whether it is confined, concealed, or in open air, is also important. There are also the factors which is the length of the cable. We mentioned this before. The length of the cable is something like the length of the pipes. The voltage of the cable is similar to the pressure into the pipe system. The longer the distance, the longer the volt drop of the cable. And hence you want to use a larger cable, right? It's a long distance travel. There's also depending on the types of the cable, right? You have PVC cable, you have UPVC cable, you have armor cable, right? So it depends, and also it depends on the voltage, right? To determine the cable sizing, you have to consider a lot of things here. Now, number 4, let's talk about system protection design. The rule for protection. The basic idea is the cable must be able to provide a current higher than MCB or fuse we discussed before. That's why you have in this table, I think, let's move back to this table, right? You found that for the 10 MCB breaker, cable size 1.5, the current is actually 17 amp. So anything less than 17 amp, you can provide by this cable. More than that, you need to choose the bigger size of cable, yeah? Or this, right? So the basic idea is the cable size must provide a current higher than the MCB. In our case, the MCB is 10 amp, the cable is 7.17 amp, right? That is the proper protection device, such that in case there's overcurrent by the device, the breaker or the fuse would break first of all before the cable being burned out or short-circuited. Okay, so the next one is about, for example, if a server, which is just for example, is 1000 watts or 1 kilowatt, if you divide by the 220 volt, you got a current around about 5 amp. So the MCB and fuse must be either 5 or bigger than this 10 amps, right? I think in this case you can choose a 10 amps, which is more safe. But you can choose a 5 if you don't mind the stripping frequently. Then the cable size, because it's only 10 amp, so the cable size shall be 1.5 mm squared first, like this cable, yeah, 10 amp. You need that. However, if you want, you can use the higher cable, right? Highest size of the cable, right? To protect the protection device if you want it. But I think here in this case, if you only need about 5 amps, right? Your 1.5 mm square cable should be sufficient because 1.5 mm square cable can provide something like 17 amp maximum. Okay, the other points to note is that the common MCBs are usually 5 amp for MCB, 10 amp, 15, 20, 30, 45, 60, 80, 100, 120, 150, and 200 amp. More or less about 200 amps of stock. If it's more than that, you can use other breakers, right, or fuse. And the next one for MCCB, you can usually take a 30 amps, 45, 60, 80, 100, 120, 150, 200, 250, 300, 350, 400, 450, 500, and then 600. There's no 700, it's only 800, and then 1000. This is the manufacturing product available. For minor fields, you can use a 1 amp, 2 amp, 5 amps. Oh, you ask, where can I find 1 amp, 2 amp, 3 amp? Okay, yeah, sometimes it could be in your microwave, right? You may only use 1 amp or 2 amps, right? Or even 5 amp for washing machine, maybe, right? But the minor fields usually can have 1 amp, 2 amp, 5 amp, 10 amp, 13, 15, 20, and 30 amps. Major fields, oh, I'm jumping too fast. Major fields can be 45 amps, 60 amp, 80, 100, 120, 150, 200, 200, 250, 300, and then every 50 up, all the way up to 2000 amp, or 2500, or 4000, I think, at the most. Okay, so now let us think about the backup fields for MCB or MCCBs to protect a 30 amp. To protect a 30 amp, suppose you have a MCB of 30 amp or you use an MCCB for 45 amps. The protection device behind or protecting this 30 amp MCB or 45 amp MCCBs, for example, it need at least 1.8 times or 2 times basically. So if you have a 30 amp MCB, you want to have a backup fuse or MCB to protect that 30 amp fuse, you might need 2 times of it. So that means you could use at least 30 times 2 is 60 amps to protect that 30 amp. Or you can use, if you have a 45 amp MCCB, you 2 times that one to 90 amps, right? But of course, there's some other factors comes in, but basically you should multiply the backup fuse or backup MCB device, circuit breaker device to the downstream is normally equals at least 2 times the largest downstream device current rating. That's a good practice on this. For example, how do we back up the fuse here for one 30 amp circuitry and one 45 amp circuitry? So in this case, we pick the largest one instead of the lowest one, or add them up together. First, we take the largest one and multiply by 2 first of all, which is 90 amps or 100 amps, right? I'm not sure there's only 90 amp, but 100 amp. So this 100 amp will be providing the backup for the 45 amp fuse comfortably, because you got 30 and 45 amps, but of course you don't add them up together. But even if you don't add it up together, it's a better choice. You can try to use a because the downstream, the largest of the downstream multiplied by 2 is 90. So in this case, you choose 100 amps as a protection device to the 45 amps MCB and a 30 amp MCB. Okay, so that 100 amp fuse will provide sufficient protection device for the 30 amp fuse or the 45 amp fuse. Okay. Now let's move on to the next one, which is about the Q&A. Let's talk about Q&A. Now suppose Q1, right? Use single phase or 3 phase is better. Well, if the power is larger than 3 kilowatt, as we mentioned before, if the device is more than 3 kilowatt, it's better to use 3 phase because it's more powerful, more efficient, less cable size, less money maybe. Although use 3 different cables instead of 1 cable now. Number 2, when should we use the power factor in the calculation, right? Whenever you see the unit is in watt W, except it is a heater or heater related lamp, then the power factor equals to 1. Otherwise, you assume power factor equals to 0.8 or 0.9, or better still, we find out the catalog, right? What's the power factor for catalog? Number 3, do or does LED and fluorescent lights have a power factor? Yes, LED also got power factor, but it's very small, 0.95 or something, close to 1. Fluorescent lights, right, again, it's more like a LED lighting. However, you find that for fluorescent lights, you have to multiply, for lighting, you have to multiply by 1.8 in general. Right. However, but for the power factor wise, right, because it's a heat resistant type of fittings, then its power factor is usually very high, it's 0.95 or close to 1. And therefore, the power factor can be ignored. But if you want to do a more calculation, more detailed calculation, yes, take the wattage and the power factor into account. What is the difference between kVA and kW? Now, I think we talked about this already. kVA is the input power from the power source to your electrical switchboard. Kw is the output power after taking into the kVA. Right, so the output power is the actual power or the available power. You have to make a ratio of 0.9. There's a difference between when you multiply 0.9 or divide by 0.9. You use kVA times 0.9, for example, that would give you the output power kW. Right? So that should be quite simple, right? Let's move on. Q5, can anyone do the electrical design before the installation? Well, most countries will require qualified electrical design engineer for safety and responsible design. So the answer is you cannot. Or this picture, okay, this picture is lost now. Let me see if I can. Yeah. All right. Okay. Is there a handbook for design? Yes. Almost every country, the government has a guide. For example, a guide for the electrical design. So, like in UK, you have the IED regulations. Right? If in Europe, you have a British Standard 7671. Right? So there's always a guide. In Hong Kong, they have their own electrical guidebook, which is mostly based on the IED regulations anyway. Number 7, the calculated result is always correct and absolute. No, the result has to be seasoned by the practical experience and common sense. Right? I have a case where a new electrical design engineer have using the computer to make the calculation, then find out that the socket outlet requires a ring circuit requiring 4 mm square cable, and ask him why you use a 4 mm square cable for a ring circuit, which is 2.5 is already enough. Well, is that based on a calculation from the computer? Yeah, well, that's from the computer, but that you have to make your own common sense, because a 4 mm square cable in a ring circuit is very difficult to be mounted onto the socket outlet at the back. To mount the 4 mm square cable into the socket outlet is quite difficult. Not to even mention about 6 mm square cable. If you calculate it, result to be 6. So whatever the calculation is, you must make your experience, make your reasonable common sense. Number 8, if we have 20 lamps, 100 watts each, will that be calculated to 2,000 watts? Well, basically, if you have 20 number of 100 watt, so the calculation has to be like this, right? In 2 separate circuits, you don't want to have 20 lamps all into one single circuitry. You want to separate 20 lamps into at the most 10 lamps only. By the same token, for the fluorescent lights as well, same. You try not to use one single circuitry to link up with more than 10 number of fittings, because you don't want, if that breaker or fuse tripped, all the lighting goes off. Right? You want to separate it, make a safety contingency. Anything more than 10 number of light fitting, you separate into more than one circuitry. So in this case, you take 2 separate circuitry for this 20 number of lamps to make it one circuit for 10 number of lamps, and this circuit for another 10 lamps, make up 20 lamps. But don't forget, there's also diversity factor here. Not all 10 lamps, 10 fittings will be switched on. You don't want to switch on the light fitting in the living room, and then the kitchen, and then the dining room, and then your bedroom, and all the same time. No, you know, there are diversity factor comes in. Diversity factor means not every lighting or every power socket being turned on. So here in this case, I think instead of because 2000 watt, you if you use the formula P equals to V times I, then The total voltage is 20 times 100 watt, which is 2000 watt. Divided by the voltage 20, 220, you got 10 amps. But here, as I mentioned, you only want to 10 amps, a 10 number times 100 only. Make it 2 circuitry. So if you use 10 times 100, you have 1000 watt. Divided by the 220 volt, you got a 5 amp. Right? So you have 2 circuitry in theory, 2 circuitry each of 5 amp. Instead of 1 circuitry of 10 amps, you make it into 2 separate circuits. However, you'll find that most lighting, MCB or fuse, they will use a 10 amp instead of a 5. Even your calculation is 5. That's based on, in case you need to add more lighting in future. So you better use the larger circuit breakers or fuse. Even it's less than 10 amp. Here in this case, instead of 2 times 5 amp fuse or MCBs, use 2 times 10 amp instead. All right, I hope you understand. There's some allowance here. Number 9, how do I know the design calculation is correct? Well, always ask for opinion from an electrical engineer to check the design carefully. Like once I've done a design for a government building, but then when I supervise the engineer to do this, they forget about, because the fluorescent lamp, there's a choke there, and also the harmonic and all these things. Actually, there's a factor of 1.8 which we need to multiply onto those fluorescent lamps. But we missed that out. But luckily, the cable size still able to make it. So always ask for a qualified electrical engineer to check the design. Number 10, how can I learn further in electrical design? Well, of course, as I mentioned, you attend practical design courses in the local market in your home country. This is possibly not as simple as just reading the standard or just a handbook, but you need a lot of actual experience, tips, lesson learned. Right? So must attend courses, especially for electrical things. Okay, so I think that's all for this. Oh, there's one more. Okay, so in summary, for a single phase using 110 volt or 220 volt, the formula is power equals to V times I times the power factor. Always put the power factor there now. The power factor could be 0.8, and P is in wattage or kilowatt, I is in amps. For three-phase supply which using 200 volt or 380 volt, the equation becomes power equals to 1.73, which would be square value times the voltage. This voltage is the single phase or three-phase voltage. Actually, it's a three-phase, right? So it's a three-phase voltage. 380 volt put into here, not 220 volt, not single phase. Times I times the power factor. Oh, you would ask, why does 200 here? Oh, in some Asia country or in America, they use the 200 volt as the three-phase voltage, right? They use three-phase voltage 200 or two-phase voltage sometimes. For example, in Taiwan, they have a three-phase voltage using 220 or 200 volt. Output power kilowatt. Now you know by this time after completing this course. The output power is in terms of always in kilowatt. The input power is always in terms of VA. VA or kVA, output power is in watt. So kW equals to kVA times the power factor. And kVA is input power. Okay, so I think you have a very good discussion in this lecture regarding the simple electrical design. Knows a little bit about the electrical cable sizing. So this is table summarize all these things. Okay, so let us look at one exercise very quickly to see how much you can recall here. Let me move to the exercise. Give me a second. All right. This exercise here. Okay, so let's look at the exercise. Exercise 1 here is always good to look at the exercise. Okay. Now, okay, so see if I can make it smaller here so that you can see better. Too small. Okay, all right. Exercise 1 for data center system design. This is a level 2 course, right? In a large data center, how do you design the normal electrical power? Well, there are. Okay, let me give you 1 minute to think about it first of all. Let you think about it, right? 1 minute. Okay, the 1 minute is up, right? Okay, so of course, this not as simple as this, right? Actually, we have to go through a more complicated exercise here, but I think if you can go on to our next level 3 data center course, right? We'll talk in more detail, but here we can do it very simple. First of all, you have to consider the lighting and power, as I mentioned before, right? The lighting and power in the data center, which is based on something like 15 watts to 20 watt for the lighting, and the power, including the normal air conditioning, right? You can use either 40 watt or 90 watt per meter square. That's the general lighting and power air conditioning. Lighting for 15 to 20 watts, air conditioning and power usually about 40 to 90 watt per meter square. But don't forget, if it is a data center, you have to put in the actual racks power. For example, if you know the number of racks, you can base on each rack could be either 2 kilowatt or 4 kilowatt or 6 or 8 or 10 or 20 or 40 kilowatt per rack. Right, that's the normal power, of course, right? And then the air conditioning. Suppose you have a rack of, make it easy, for a rack you have 2 kilowatts. Right, so can I do this one? Let me see, Yeah, so you have to think about the lighting, yeah, about say 15 to 20 watt per meter square, right? And then the power, including some AC unit, then it could be say 40 to 90 watts per meter square, yeah, per meter square, yeah, cool. Plus the crack, plus the rack power each. right? It can be say 2 kilowatt up to say 40 kilowatt each. Then you multiply by how many number of racks, right? Now, suppose you have, well, make it easy, right? Suppose you have 100 racks, each about, make it easier, 10 kilowatt, okay? Then the cooling load, right? Cooling load is equal to almost that 100 times 10 kilowatt, which is equals to, I think it's 1000 kilowatt cooling. And 1000, let's put a bracket here, okay? So that is equals to almost, use the 1000 kilowatt cooling divided by 5 as a ratio. That equals to, I think, 200 kilowatt electric. No. So that's how you estimate the power for the crack unit. Right, 200 kilowatt electric, and you have another, say, 100 kilowatt. Right, 100 here. The electrical power equals to 1000 kilowatt electric. Yeah. So you add up all this, right? The lighting and power, and then the rack power, and then the cooling load divided by 5 to get the electric, right? And then also allow for some safety factor or future expansion, or say 10 to 20, or to even some people put 50% on top. Yeah. So that is how you did it for a normal electrical power. This is normal only. All right. For the UPS and for the essential power, we'll talk about it some other time because it's quite a complicated one, or lengthy. Actually, it's not complicated. Now, how to size the generators? By the same token, let us take the IT load here. For example, right? If we have a 100 rack, right, using 10 kilowatt each. So the total power is 1000 kilowatt, right? Electric, okay? Electric. And suppose you have some other essential power for the fire and security or lighting. For example, you may want to allow for another 10 to 20% on top, right? Okay. But don't forget, at this moment in time, your genset also provide for the crack unit or chiller plant. But let's make it a crack first of all. So in the above case, right, you need a crack of 200 kilowatt electric. Yeah. So what do you get here now? So I think the total roughly is equals to 1000 kilowatt plus, that's the rack, plus the crack unit, which is 200 kilowatt. Yeah, for the crack. The 200 comes from here, 200 kilowatt E. Yeah. So that adds up equals to 1,200 kilowatt electric. And then you multiply the actual one, right? Actual one. Use 1,200 kilowatt multiplied by, say, allow for 20%. So that gives you, I think, if I use my phone to calculate this, 1,200 kilowatt times 1.2, you got something like 1,440 kilowatt. So, but that is the essential power only. Yeah. However, again, the genset itself got its own problem, right? So the genset got its own problem. So what we could have done here, we use 1,440, 0 kilowatt, multiplied by 1.3 to allow for any transient. And then you want to also give some spare capacity. Say you want to multiply by 1.2 as well, 1.1, sorry, to give spare capacity. 1.3 is for the transient, right? And 1.1 is for the, if I'm not mistaken, 1.1 for some spare capacity. So that gives you, I believe, and then of course you want to divide by the power factor 0.9. Yeah, for a power factor. So that should be equals to, if I'm not mistaken, 1,440 times 1.3 times 1.3 for the transient loading, times 1.1 for spare capacity divided by 0.9. I think you got 2288 kilowatt, if I'm not making a mistake here. Or actually, that's a kVA, okay? Because we have multiplied by the divided by the 0.9 factorial. So in this case, conclusion is you shall go and buy a genset of 2,500 kVA. Yeah, but that's wrong. You know why? No, we have this 2,500 kVA generator, okay, but you don't want to have one single generator, right? You want to have make it say 5 or make it say 2 number. Say use 2 number. 2 times 1,250 kVA genset. Maybe better. Yeah, to make it 2 or n plus 1, right? If you want to use n plus 1. N plus 1 means, in this case, you need 3 number each, 3 genset each number, sorry, each number is 1,250 kVA. In case one breaks down, you still got the other 2 working. All right, so that should be quite simple. Okay, how much power required for the cooling at the IT load, right? Basically, I think 1 kilowatt IT load, you can, quite simple, you can assume 1 kilowatt cooling, right? 1 kilowatt electric, let's put it that way. I'm sorry, I put sometimes large W or sometimes small w, right? Okay, or the other way around. But that's the general rule of thumb. But don't forget, you need to add other heat dissipating heat flow, like 2.5 to 5% of the UPS, right? Heat load. Or any heat load that you know. Inside the server. For example, the lighting, for example, but it's very small usually. Or the batteries, for example. Yeah. Okay, so but all this you can find out, right? Okay, almost back now. Oh, UPS. Oh, geez. Okay, the UPS, right? In this case, if we base on assume the IT load, same thing. Assume the IT load is 1,000 kilowatt electric. Yeah, I'll put electric here. Then add spare capacity of say 20%, for example, or add UPS for fire and security or others loads. Right, so make it another 10%, for example. So in this case, the UPS load oh, 20%, yeah. So here we add the other load. Say another 10%, just for rough estimation. So in this case, total equals to 1,000 kilowatt times 1.3, which is equal to 1,300 kilowatt UPS. Yeah, round, because you also want to have not just one single UPS. You want to have at least more than one UPS. So here maybe you can use let me see, you can use a 5 units, right? You can use 5 UPS, each about 300 kilowatt. Yeah, that should be allowed for sufficient, including any spare or future expansion. You want to save the space and time and money now to add a bit more. All right. Oh. Okay, so what is the n+2 system? I think we discussed about this before, right? The n+2. So in the case above, actually, this looks like already a n+1 already. So n+2, in this case, it is 6 units each 300 kilowatt. Yeah, this is the n+2 system. Now here we talked about the fire and circuit system doesn't need a separate generator system. Normally does not require unless the local country code may require. Just use the same UPS or just use the genset above. That should be enough. All right. Okay, so I think we have almost finished now. So I hope you understand how we arrived to these things. There may be some calculation error here, but I try to make it as accurate as possible. But that's the way that you want to do it. I hope you enjoy this course and continue with the next module. The next module will talk about air conditioning installation, something like that, right? And I hope you enjoyed it. So thank you very much. Thank you very much today, and I'll see you again next time. Right? In this course, this data center system design for engineers and managers, we have 5 modules. Right? So I'll see you next time. Thank you. Bye bye.